Welcome back to the Deep Dive. Today we're plunging into something, well, foundational, but often kind of invisible in our digital lives. You just think about the sheer volume of data. It's overwhelming, right? Washing over us every single second. Everything from your social media feed, every scroll, to this constant stream from billions of IoT devices. It's massive, a huge, ever-growing flood. And yeah, it's a colossal challenge, but also, an incredible opportunity for insights. Okay, let's unpack this. So organizations, they're all racing to make sense of this big data. They want to store it, analyze it, turn it into some kind of edge. But here's the really basic question, the one that kind of underpins everything. How do they actually store all this stuff efficiently so they can query it fast? And crucially, not go broke doing it. Because, let's be real, data storage costs add up fast.
And that's exactly where our unsung heroes come in. File formats. You see, the choice of file format for big data, it's not just some minor technical detail for the IT folks. No, it's a really strategic decision. It impacts everything, your cloud bills, how fast your reports run, even how flexible your data can be down the line as things change. And what often gets missed is that the formats we know, like CSV and JSON, they're familiar, sure, human readable, but they just weren't built for this kind of massive scale. They tend to, well, eat up resources unnecessarily when you're talking petabytes. They become a bottleneck, a huge one.
And that's our mission today, isn't it? We're going to try and cut through that complexity. We'll explore the characteristics, the good parts, the bad parts of these big data file formats like Avro, Parquet, ORC, and Iceberg. By the end of this deep dive, hopefully you'll have a much clearer picture of how these things work, why picking the right one is so critical for any data operation, and how these seemingly tiny tech choices have these massive ripple effects on the business.
Exactly. So let's start with that core problem. Why do those familiar formats, CSV, JSON, why do they struggle so much with really big data sets? Okay, imagine a company database. Every customer record, every transaction is just a line of text. They're text-based, yeah, human readable seems handy at first, but it means they lack the efficiencies you get with binary options, and it also means they don't compress well. Not efficiently. So you end up with this massive storage footprint on your servers, in the cloud, wherever. And beyond just size, they're fundamentally row-based. What that means is, let's say you only need one tiny piece of info, like just the purchase amount from a transaction record. Well, the system might still have to scan the entire row, the whole record, customer address, product description, everything irrelevant, just to get that one number.
Wow, okay.
Yeah, it massively increases I/O, CPU load, memory use. And JSON, for instance, with all its nested data, it can be super CPU intensive just to parse. A huge bottleneck, especially if you only care about a tiny fraction of the data in there. It's not what they were built for, not at this scale.
So what you're really highlighting there is that these technical choices, they hit the bottom line, right? Directly.
Yeah.
Tangibly. That's maybe why your cloud storage bill is way higher than you expect, or why that critical report you need takes like hours instead of minutes. Choosing the wrong file format, or maybe it's a suboptimal one, it really can mean higher costs, slower processing, and real headaches trying to manage data when structures change. It's kind of a big aha moment, isn't it? It explains why some apps feel snappy and others just crawl.
Precisely. And to tackle these challenges, big data file formats have evolved quite a bit. They generally fall into, let's say, three main categories. First up, we have row-based formats. Okay, these organize data by rows. Each row holds a complete record. They're optimized for things like transactional stuff, where you often need the whole record to access or modify it. Good for fast sequential reads, too, like writing logs. Avro is a key example here.
Okay, row-based. Got it, like a traditional list.
Then second, there are column-based formats, or columnar formats. These store data by columns, so all the values for one column are stored together. This lets the system read or write just specific columns very efficiently. They're optimized for read-heavy analytical queries. Think data warehouses. You scan tons of rows, but maybe you only need a couple of columns.
Okay.
This is really the engine behind modern analytics platforms like, BigQuery or Redshift. And Parquet and ORC, they're the heavy hitters in this category.
K and ORC. Column-based.
Right. And finally, the third category. Table-based formats. This is a newer evolution designed specifically to deal with the messy challenges of managing huge amounts of data in these dynamic data lakes. They add really crucial features like A/C/D transactions. That's atomicity, consistency, isolation, durability.
Database stuff, basically.
Yeah, bringing database-level reliability to your flexible data lake, even with lots going on at once. Huge operations. And they also enable fancier things like partition evolution on top of the underlying files. It's a smarter management layer. Apache Iceberg is a leader here.
Okay, let me see if I can use an analogy here for row versus column. That's right. Imagine a giant library, right, with info on every book ever. A row-based format is like each book's catalog card has everything on it. Title, author, publication date, genre, ISBN, all together on one card. But a column-based format is like, okay, all the titles are in one massive section of the library. All the authors are in another section. All the publication dates in a third.
Exactly.
Now, if you just wanted to count how many books came out in, say, 2024 across the entire library, which way is faster?
Just scanning the publication date section, right?
Yeah. You just go to the publication date section. You don't need to wade through all the titles or authors. That's the core idea.
That's the core idea, precisely. Big efficiency gain for analytics.
Cool. Okay, so with those categories clear, let's pull out that first specific tool, Avro. You called it an agile streamer.
Right. Avro. It's a compact binary format, primarily used for data serialization. It's really good for communication protocols, like sending data between systems, and also for storing data in HDFS, the Hadoop distributed file system. That's kind of the bedrock storage for a lot of big data stuff. Now, what really makes Avro stand out is its excellent schema evolution capabilities. It's great at handling changes, additions, modifications to the schema without forcing you to rewrite all your existing data.
Okay. That sounds useful.
Very useful. It makes it ideal for dynamic environments where schemas change a lot. Think real-time pipelines using Kafka. You often add new fields on the fly, right? Avro ensures those changes don't break everything, keeps the data streams flowing. Very important for compatibility.
Okay, yeah, that makes total sense for streaming data stuff that's always morphing. But what happens if a company messes up? Like they try using Avro for their big, heavy analytical reports.
Yeah.
What's the first pain point they'd feel besides just slow queries?
Yeah, good question. The main headache, honestly, would be cost and just. Agonizingly slow analytics. Avro's compression is, well, lower, around 40–50% reduction typically, compared to columnar formats, which can hit 70–80% or more. So first off, you're paying more for storage.
Right.
More storage, more money. But more critically, it's less efficient for analytical queries because it is row-based. So take your example, quarterly sales report needs total amount and transaction date from millions, maybe billions of records. Avro forces the system to read everything else in each row too, customer name, product ID, address, all of it, just to grab those two numbers.
Ouch.
Yeah. It's a massive waste of I/O. Processing power directly leads to higher cloud compute bills and very frustrated analysts waiting around. Plus, it doesn't have native partitioning support built in, which just makes managing really large data sets even trickier.
Okay, so Avro's the champ for flexible, fast-changing streams where schema agility is king. But what about when you need raw power, sheer speed for those deep analytical dives? That sounds like where Parquet comes in, the powerhouse.
Exactly right. Parquet. It's an open-source columnar storage format, purpose-built, really engineered for high compression and super fast analytical processing. It's pretty much become the default choice for many modern data lakes for good reason. It brings several huge advantages. First, highest compression ratios. Often you see 70–80% reduction on structured data, sometimes even more. That hits your storage costs directly. Big savings.
70–80%? Wow.
Yeah. And more importantly, superior query performance, especially for read-heavy analytics, aggregations, filtering, Parquet flies. In environments like Spark or Hive, benchmarks often show Parquet being maybe 10–15% faster than ORC in complex scenarios. And here's the really clever bit. Predicate pushdown.
Predicate pushdown.
Yeah.
Okay, explain this magic trick.
So Parquet stores extra information, metadata, within the file itself. Things like the minimum and maximum values for columns within each chunk or block of data. This lets the query engine be smart. It can look at the metadata and say, hey, this whole block of data doesn't have any values matching the filter, so I'm just going to skip it entirely. Yeah. It literally avoids reading data it knows isn't relevant. This can slash I/O by like 50–90%. Think about a financial firm querying billions of trades. They only want transactions between 9 a.m. and 10 a.m. on Tuesday. Predicate pushdown lets them skip potentially massive chunks of data from Monday or Wednesday or even other times on Tuesday. Makes queries way, way faster, almost real time sometimes.
Okay, that is seriously clever. Avoid reading data you don't need.
And beyond speed, Parquet also has the broadest compatibility. It's supported pretty much everywhere. Spark, Hive, AWS Athena, Google BigQuery, Trino, Presto, Flink, you name it. This makes it super versatile for multi-platform architectures. It's a safe bet, helps future-proof your stack, and yes, it does support schema evolution too. You can add new columns without rewriting everything, though maybe not quite as flexible as Avro or Iceberg if you need to modify existing columns often.
Wow, okay, that predicate pushdown, that feels like a game changer. For speed, for cost. Imagine you've got, I don't know, a 10 terabyte IoT data set, hundreds of sensor readings per record. With Parquet, analysts could maybe read just 2 out of those 100 columns for their report, cutting scan time from potentially hours down to maybe tens of minutes. And that's not just a tech win, right? For a logistics company, that can mean optimizing routes minutes faster or predicting equipment failure sooner. Real bottom line impact.
Absolutely. It bridges that gap between technical choice and business value. Okay, moving on to ORC. Optimized row columnar. This is another self-describing, type-aware columnar file format like Parquet. It originated in the Hadoop world, actually, specifically optimized for Hive initially, but now it's more general purpose, often seen as Parquet's main competitor. ORC also delivers high compression. Very comparable to Parquet, again, typically in that 70–80% reduction range. So great for data warehousing scenarios, keeping storage costs down.
Okay, similar compression.
Yeah. And it offers excellent query performance too, especially for analytics, particularly strong in Hadoop-based systems like Hive. Sometimes it even edges out Parquet there for certain queries. And this brings up an interesting point about strategy. Sometimes raw speed isn't the only factor. Cost matters, right?
Always.
On Amazon Athena, for example, ORC can often be the most inexpensive format. Why? Because Athena charges based on the amount of data scanned. Since ORC files are highly compressed, super small, even if the query takes, say, a fraction longer to run than maybe a compressed CSV, the total cost based on data scanned can be much lower. There was a benchmark, I think, where a 5.2 gigabit dataset was 1,388 millibeats in CSV, but only 332 millibeats in ORC. That's a huge difference in scanned data costs for frequent queries.
That's fascinating. So even if it's not always the absolute fastest on the stopwatch, sometimes being the most cost-effective per query is the real win.
Especially in the cloud, yeah, where every byte scan hits your bill. But what are the trade-offs then? Any big downsides compared to Parquet? It does have a couple. ORC's schema evolution is more limited. It mainly supports adding new columns easily. Modifying or deleting existing columns, that can be trickier, often requires rewriting data. And its platform compatibility is generally narrower than Parquet's. It's very strong and optimized within the Hadoop ecosystem, definitely. But Parquet just has wider support across different platforms and clouds. So, if your world is heavily Hadoop-centric, ORC might still be your best bet.
Okay, got it. Strong in its niche, maybe less universal than Parquet.
And finally, let's talk about Iceberg. Now, this one's a bit different. While Avro, Parquet, ORC define how data is stored inside a single file, Iceberg is an open source table format. Think of it like a smart management layer sitting on top of potentially thousands or millions of individual data files, which could themselves be Parquet or ORC files.
So it's like the catalog or the index for the data lake?
Kind of, but much more powerful. It creates a robust, reliable table structure across your whole data lake. It was specifically built to fix the limitations of traditional data lake architectures, which often struggled with things like consistency and reliability, especially when lots of things were happening at once. Iceberg brings some really significant advantages. First, ACID transactions.
ACID, like
Exactly.
databases have.
Exactly. It ensures data integrity, consistency, even with huge concurrent operations happening on your data lake table. Multiple users, multiple processes can read and write safely without corrupting the data. That was a huge pain point in older data lakes. It brings that warehouse-level reliability. It also offers the strongest schema evolution capabilities we've seen. It handles additions, modifications, but also, crucially, partition evolution.
Partition evolution, what's that?
Okay, partitioning is how you physically organize data on disk, maybe by data region to speed up queries. Partition evolution means data engineers can change that organization scheme later, maybe switch from daily to hourly partitions as business needs change, without rewriting all the old historical data.
Whoa, that sounds hard and useful.
It's a monumental engineering feat, yeah. And a massive cost saver. Huge for agility. On top of that, Iceberg supports data versioning and time travel.
Time travel, like Back to the Future.
Sort of. You can roll back your table to a previous state if something went wrong, or you can query the data exactly as it looked at a specific point in time in the past.
Wow.
Yeah, it's incredibly powerful for auditing, governance, fixing mistakes, comparing changes, a real game changer for data integrity. It also excels at efficient partitioning and data pruning, especially for these massive partitioned data sets you find in cloud data lakes. And it's flexible too. Works with multiple query engines, Spark, Flink, Trino, and like I said, it can use different underlying file formats like Parquet or ORC to actually store the data bits.
Wow. Okay, Iceberg sounds like a serious upgrade for data lakes. That ACD guarantee, the time travel, being able to roll back your entire data lake if someone makes a huge mistake. That's huge. And this partition evolution you mentioned,
Yeah.
what does that really unlock for the people managing the data? Does it mean they're not, like, trapped by decisions they made years ago about how to organize stuff?
Precisely. They are no longer trapped. That's a great way to put it. In the old days, if you partitioned by year and later realized, oh man, we really need year, month, day for performance, you were facing a massive, costly, time-consuming rewrite of all your historical data. Just brutal.
Nightmare.
Yeah. With Iceberg, you just evolve the partition spec. It updates the metadata, handles the transition smoothly. Old data stays where it is, new data uses the new scheme, but the query engine sees it all as one unified table. It gives you incredible agility, reduces that engineering burden massively, allows the data structure to evolve with the business needs. So, okay, if we kind of zoom out and connect all these dots, you can really see that no single file format is optimal for all scenarios.
Definitely not.
The choice really depends on your specific needs, your workload patterns, what systems you already have in place. So when you're making this decision, you need to consider these key things. First, storage efficiency and cost. If cutting those cloud storage bills is top priority, columnar formats, Parquet and ORC, they're your friends. That 70–80% compression makes a huge difference.
Okay, cost, focus, mass, Parquet, ORC.
Second, query performance, and specifically read versus write. For read-heavy analytics, think BI dashboards, big aggregate reports. Yeah, Parquet and ORC are generally your best bets. Super fast reads. But for write-heavy stuff, like real-time streaming ingest or ETL pipelines that do fast sequential reads and writes, Avro is often ideal because of its write performance and schema handling.
Right. Read-heavy, Parquet, ORC. Write-heavy streaming, Avro.
Third, schema evolution. How much does your data structure change? If it's constantly in flux, adding fields, modifying them, maybe even deleting them, then Avro and especially Iceberg offer the most flexibility. If your schema is more stable, maybe just adding new columns occasionally, Parquet and ORC handle that fine.
Got it. Changing schema, Avro, Iceberg. Stable schema, Parquet, ORC. Okay.
Fourth, partitioning needs. How complex is your data layout? For really complex, large-scale data lakes where you might need to change how data is partitioned over time, Iceberg is superior with that partition evolution feature. Parquet is also very effective, though, especially with its predicate pushdown on fixed partitions.
Complex partitioning, Iceberg. Standard Parquet works well.
And finally, fifth, platform compatibility. Where does this data need to live and be read? If you're in a multi-cloud setup or just have a diverse mix of tools, Parquet's really broad compatibility is a major plus. It just works everywhere. If you're deep in the Hadoop ecosystem, ORC might be highly optimized for you. And for streaming platforms like Kafka, Avro is a very natural fit. And remember, all these technical choices, they have that big picture impact, right? They translate directly to faster insights, lower infrastructure costs, more agile data management, better business outcomes.
So what this all really means for you, listening, is you got to understand your data, right? Your workload. Even your budget. It sounds like picking the right tool from a really specialized toolbox instead of just trying to use, I don't know, a hammer for every single job. So if I'm, say, a data engineer starting a brand new data lake project, I need something versatile, generally solid. Is Parquet often that sort of go-to starting point? And then maybe I specialize from there. Bring in Avro if I have a big streaming component, or layer Iceberg on top if I need that heavy-duty table management.
That's actually a very practical rule of thumb.
Yeah.
Parquet has really earned its place as a strong general-purpose default for analytical workloads because it hits a nice balance. Good compression, great performance, excellent compatibility. It's often a safe place to start. Then, exactly as you said, you'd bring in Avro specifically when schema evolution in a streaming context is your absolute top priority. And you deploy Iceberg when you need those database-like guarantees, the ACD transactions, the time travel, the partition evolution, particularly in a complex data lake environment. And often, yeah, you'll still have Parquet files sitting underneath Iceberg. It really is about diagnosing your specific problem accurately and then selecting the tool that's truly optimized for that job, not just the one you used last time or the one that seems simplest initially.
This deep dive really highlights the incredible evolution, doesn't it? From just simple text files like CSV to these incredibly sophisticated binary structures, each one designed to tackle very specific, very massive challenges. Hopefully, this gives you a much better appreciation for the nuances of big data infrastructure and why these decisions, often hidden away, are so critical for the kind of fast, responsive digital world we all just expect now. It's kind of amazing to think how foundational these choices about just storing bits really are.
And what's truly interesting now, I think, is looking ahead. As data keeps exploding, volume, velocity, and new tech trends emerge. Think decentralized storage, more serverless compute, even more real-time analytics. These file formats, they're going to have to keep evolving too. The lines between them might even blur more. Or maybe we'll see entirely new approaches emerge to handle data problems we can't even quite imagine today. The innovation isn't stopping.
Yeah, the quest for efficient data, it's definitely not over. It feels like it's just getting more and more fascinating. So maybe consider how these choices, way down in the infrastructure stack, impact the apps you use every day. The recommendations you get, the insights companies derive, the decisions being made all around you, often silently powered by these formats. What new file formats might we even see in the next decade? Maybe something designed specifically for, I don't know, hyper-personalized AI,
Right.
or truly immersive virtual worlds, or maybe even those futuristic brain-computer interfaces. Definitely something to chew on as you go about your day.